Hello everybody, I hope everyone is fine and all are doing well. Today I am going to discuss another GATE 2024 question where there is a full scale sinusoidal signal which has been applied to a 10-bit ADC. Okay, so there is a term full scale. So when I will discuss on dynamic range, when I will define the block diagram of ADC over there, I will explain about this term, that what does this full scale means. So let's come back to the question. So there is a sinusoidal signal which is a single tone signal. So whose frequency say is Fin and has been applied to a 10-bit ADC. Let me explain this in frequency domain. A single tone is applied, okay, and that has been applied to a 10-bit ADC. And over there it has been already mentioned that there is a total noise and a distortion. Okay, so in the output, what you will get the fundamental component and the distortion component and the quantization, say quantization noise component. And other than that, there can be some other components also. As you see in the FFT if you connect a 1 ohm load resistor at the load output, then the fundamental signal component in the ADC output has a normalized power of 1 watt. And total noise and distortion normalized power is 10 microwatt, which is 10 into 10 to the power minus 6, that is 10 to the power minus 5 watt. So here the total noise means say quantization noise, jitter noise, thermal noise and etc. Okay, if only quantization noise, say for only uniform quantization is present and input is sinusoid, this 10-bit ADC will have effective number of bits equal to 10-bit. That is my resolution. But since there is a distortion and might be some other noise other than say quantization noise, so there the effective number of bits will be lesser than 10. This I will explain now how it is occur. So that is the reason for which they have asked you to find out the effective number of bits, because there is a total noise and then there is also a distortion. Say that the effective number of bits will be lesser than 10. But what is the exact value? Okay, so I will explain now that how it is occurring and how much means what will be the exact number of bits, and it will be less than 10. So for that, I should go to some basic concepts. Okay, so the first topic which I'm going to discuss right now is the block diagram of the ADC. After that, slowly we will reach to that point where we can find out the effective number of bits. So let's discuss about the block diagram of an ADC. So there is a sinusoidal signal input. In reality, the input should not necessarily, it does not has to be sinusoidal. It can be of multi-tone. Single tone is been mentioned in the question, that is for just a simplicity. But in reality, we will be always doing multi-tone signal or a signal which has multiple frequency component. Okay, there is a sinusoidal input, which is a single tone, say A cos 2 pi f in t, where the amplitude is A and the input frequency is Fin. Okay, to avoid aliasing, first we need a low pass filter so that we can eliminate the unnecessary high frequency components and only the necessary the frequency component stay in the signal. Okay, and also when we are sampling, which we will discuss in the next section, we will do the sampling. The sampling should happen in such a way so that there is no overlapping or say there is no aliasing. Okay, so this too we have to think. So in the low pass filter, the signal is given to the low pass filter when we are assuming such that this is an ideal low pass filter where the bandwidth or the cutoff frequency is equal to Fin. Okay, and then this low pass signal means the signal which has only low pass characteristics or the low frequency component is given to the sample and hold circuit. And this sample and hold circuit, while it was doing the sampling, it has to maintain the Nyquist criteria. And what is the Nyquist criteria? Nyquist criteria says that the minimum sampling frequency has to be equal to twice into the maximum frequency component which is present in the original signal. So here it is Fin, which is the maximum frequency component. So the minimum sampling frequency is twice into Fin. Here we are considering, generally in Nyquist theorem it is written that Fs has to be greater than or equal to, but for simplicity we are here for just your understanding I am considering as a minimum sampling frequency. Okay, then these sampled values are given to a quantizer. Say for simplicity I am considering that this is a uniform quantizer. When you see the sinusoidal input and say you have defined say the sampling frequency, okay, and you might get in any of the values from plus A to minus A. Okay, and so you can think that if it is say the sampling frequency is greater than 2 Fin and there is no relation between the sampling frequency and the input frequency, or say there is no relation between the sampling period or the input period. Okay, so you might have infinite amount of sampled values, okay, but you don't have so much of memory to store them, to store those values. So there is a need where you have to define them into levels, and you have to make a partition of the entire dynamic range. You have to make a partition that from this voltage level to this voltage level, we are going to define this as a particular voltage value, okay, or a particular level. So that is how the quantization, the uniform quantizer actually works, okay. As already I have told you about the term full scale. In the full scale, that what does it means? That say that the range, the peak to peak of the input signal, that is your minus A to plus A or plus A to minus A. Okay, that is a peak to peak ranges of 2A. And when we are doing the quantizer also have a dynamic range of 2A. So when we will calculate the step size of the quantizer, this dynamic range will come into the picture, which is the peak to peak value of the sinusoidal input. Okay. So whatever we are getting the levels, quantized level, that we have to change to a digital bits, because we are going to just transfer the zeros and ones. Okay. We have already defined the levels, that this voltage range will give me this voltage level. Okay, but we have to do some encoding. Say we have 1, 2, 3, 4, 5, 6, 7, 8, but we have to transfer them. So we have only zeros and ones as a bit, because this is an ADC, it will produce only zeros and ones. But how we are going to present it? So that can be only done with encoding, right? So that is like a decimal. You have a decimal code like 1 to 8 or say something 1, 2, 3, 4, 7. So that you have to convert into say a 3-bit digital data or 3-bit binary data. So that is done with an in-bit encoder. The output of the quantizer is always a quantized value. Okay. So now let us check that how we can calculate a quantization error. So the quantization error can be calculated that if we subtract the quantized value with the original signal. Okay. So that is how we can calculate the quantization error. And now if we just rephrase this equation of this quantization error, then we can see that the quantized output is nothing but equal to the original signal with the quantization error. So it is an additive noise. It acting like an additive noise. The input output characteristics of a uniform quantizer, where you can see that if the input level is between minus del by 2 to plus del by 2, then the quantized value is 0. And if the input level is between del by 2 to 3 del by 2, then the input level is del. So you can see through quantization, we can actually limit our input to some definite levels. Here 3 del, 2 del, 0. So we are already defining the entire input range into this finite levels, or say the quantization levels. And here the del is the quantization step size, means the change in the input which is required, say from one value to another, the change required so that the quantized level has been shifted from one level to the next level. To calculate the quantization error, what we need to do? We have to subtract the input from the quantized signal. And then if we see the quantization error for the entire input range, then we will see that the quantization error is uniformly distributed between minus del by 2 and plus del by 2. Also, we can model this quantization error as a white noise. Okay, so if you see the power spectral density, it is flat with respect to the frequency. And if you see the probability density function, then you will see that it is uniformly distributed between minus del by 2 to plus del by 2. And if you do the integration for the entire range, then you will get 1. As given in the question, that the input is a sinusoidal. So if we assume, say the sinusoid is A sin omega t or say A cos omega t, then the peak to peak value for this sinusoidal is twice of A. So you can say like A sin omega t is equal to VPP, means the peak to peak value divided by 2 into sin omega t. Okay. So now if you compute the signal power, means the input signal, then you will get A square by 2, which is VPP square divided by 8. Okay, and P6, that is my signal power. Now after sample and hold, if we are quantizing the samples with an n-bit quantizer, then from 0 to plus A, we will have 2 to the power n minus 1 steps. Or we can say that within this dynamic range, or say within this peak to peak value, we have to make finite number of levels. So from 0 to plus a, we have to make 2 to the power n levels, and say from minus a to plus a, we have to make 2 to the power n plus 1 levels. So what does this mean? That between each level, there will be a quantization step size. So how many steps will be there? It will be 2 to the power n steps. So we are making this peak to peak, say minus a to plus a, that is twice a of length, equal to 2 to the power n into delta. Okay, now if we measure the quantization power, say because of quantization there is a noise created, and if you have already seen that there is a PDF, and if you integrate it, then you will get that the quantization power is equal to del square by 12. Now if we calculate the signal to quantization noise ratio, that is P signal divided by PQ, then we will get 3 by 2 into 2 to the power 2n. Now if we convert this one to dB, then we will get like 6n plus 1.76 dB. Always remember this fact, that if a single tone, a sinusoidal input is given to an n-bit ADC, which has an n-bit quantizer, and where the quantization is of uniform, okay, and you have only quantization noise, there cannot be other noise like jitter noise or thermal noise or any other kind of noises, okay, even there is no distortion, then it will get the maximum SNR, which is equal to 6n plus 1.76 dB. And only in that case, this ADC, n-bit ADC, will behave like an n-bit ADC. Means the effective number of bits will be n-bit, the resolution of the ADC will be maximum, which is n. And if other than quantization noise, if there are any other noises, or say there is distortion, then the resolution will be lesser than n, and your SNR will be also lesser than 6n plus 1.76 dB. It will not behave like an n-bit ADC, because the resolution of that ADC is lesser than n-bit. Now, if we do the numerical analysis for a 10-bit ADC, where in the first case, which is given in the left, there is only quantization noise, and in the second case, which is given in the right, you can see that there is both quantization noise and distortion noise. I am not assuming some other noises like jitter, thermal, not considering, okay, because in the question it has been said that say total noise and distortion noise, so I am considering this too, okay. So in the first case, you will see that for a 10-bit ADC, the maximum SNR which you will get, that is 61.76 dB. But in the second case, where it is a 10-bit ADC, but if you calculate the SQ and DR, means which is given like signal to quantization noise plus distortion noise ratio, you will see that 10 log P signal divided by PQ plus PD. Here PQ I means the total noise, and PD is the distortion noise, okay, distortion. So if you calculate, where you have the P signal is given as normalized power, which was given as 1 watt, and your total noise and distortion is given as 10 microwatt. So if you calculate, you will get 50 dB. Okay, so instead of getting 61.76 dB, you are getting 50 dB. So already there is a loss of 11.76 dB, and that is because of other noise contributions and also because of the distortion. This distortion might have happened in the sampling circuit. This can happen, okay. So in our first case, the resolution is 10-bit and your effective number of bits is also 10. But if you go to the second case, and if you try to calculate the effective number of bits, so it is like that there is a smaller resolution of ADC, okay, where there is only say quantization noise, means it is an ideal ADC, okay. So that means what will be that effective number of bit which is ideal, which will give a signal to quantization noise ratio as 50 dB. So that we need to find out, that is my effective number of bit. So you just need to replace your n, which is given as 6n plus 1.76, you just replace that n with effective number of bits, means ENOB, and your SNR actual is 50 dB. So now if you calculate, you will get that the effective number of bits is equal to 8 bits, is almost equal to, and that is our answer in the question. This is our answer, okay. Although it is a 10-bit ADC, but due to noise, quantization noise and some other noises which is not given, and also due to distortion, the ADC is not performing like a 10-bit ADC. It is performing like an 8-bit ADC. This is unfortunate, okay. So let me explain it in the next slide. So here you can see a same sinusoidal input is given to an 8-bit ADC where there is only quantization noise. But what is the SNR? You will get around 49.76 dB. 6 into 8 plus 1.76. And if you apply the same sinusoidal input to a 10-bit ADC, which is given in our question, which has a total noise and say distortion normalized power, so then also you will get an SQDNR of 50 dB. So I hope you have understood that how the resolution has decreased. Because of that reason, already n is mentioned as 10, but still they have told us to find out the effective number of bits. Okay, thank you everyone. And guys, if you have any problem, please share in the comment and do subscribe, do like. This motivates us a lot. And all my best wishes to everyone, to all the viewers, all my best wishes.